Right, so topic B4 is lipids, and this is what we're going to be looking at. Generally speaking, hydrophobic because they've got long carbon chains. They do have polar heads quite often. They are less oxidized than our carbohydrates, which means we can actually get more energy from them. We tend to use them though as energy stores because they're not particularly soluble. These stores can also have a protective or insulating function, for example around some of the organs like the heart. They're also important for making up hormones and forming an important part of our cell membranes and cell walls, and they can also help us absorb fat soluble vitamins. So there's three types that we're going to look at, and we'll start with triglycerides. These may be the kind you're more familiar with in terms of what you eat. And you can see here we're getting these long hydrophobic carbon chains, and we've got our carboxyl head there. And within this fatty acid we can have some double bonds, and we call those, that's a degree of unsaturation. And these fatty acids will join up to glycerol, which is here, making these ester links, which you can see up here, dropping out a water molecule each time. So it's a condensation reaction, and that's made our triglyceride. You can see here the fatty acids linking to our glycerol, water coming out, and we're making our triglyceride. So when we're cooking, we're using fats and oils. That's what these are made up of, these triglycerides. And the unsaturation in them has an impact on their boiling points and melting points. So something that's highly saturated, in other words is all single bonds, is going to form this nice straight chain like that. They're going to pack together very tightly, and as a result we get quite strong London dispersion forces, and we see a high melting point and boiling point. So something like lard would fall into that category. If we introduce some unsaturation, you can see the chains start to become kinked. Not so much here with our trans fatty acid, but if we have a cis one, where my double bond is going back on itself and the chain continues, you can see that I get these bends. They don't pack together so well, and we end up with a lower melting point. So something like olive oil will have more unsaturated fats in it. That's why that's a liquid at room temperature. Now we might decide that the fat that we've got, it's in the unsuitable state for us, and so we might want to hydrogenate that. And when we hydrogenate them, we're adding hydrogen with a nickel catalyst, and that is hydrogenating these double bonds. It's stretching out the molecules, making them more linear, better packing, better London dispersion forces, and we see a higher melting point and boiling point. We may also see some cis bonds becoming trans, and these trans fats have been linked to dangerous health issues, like low density lipoproteins, which we'll be talking about a little bit later. So continuing with the triglycerides, some examples here, linoleic and linolenic, and they are essential fatty acids because they have to come from your diet. Your body can't synthesize them, and these fatty acids have been linked with lowering those LDL levels and helping protect against heart disease. So in terms of why is this omega-6, why is it omega-3, well, it's actually a little bit unusual in that it's referring to where the double bond is, but rather than counting from the functional group, we're actually counting from this end of the molecule. So you can see this is 1, 2, 3, 4, 5, 6. That's this omega-6, whereas the omega-3 would have its double bond more in there. So these essential fatty acids are a good source of energy. They're important precursors to other substances. They can actually lift your mood, help, as I say, protect against that LDL. If we don't have enough, get a little bit lethargic, a little bit tired, and get a little bit cranky. So where do we get them from? Well, fish, pumpkin seeds, leafy vegetables, and walnuts, as you can see there. Now, the degree of unsaturation of a fatty acid can be measured in terms of its iodine number. Right? And what we've got there is iodine reacting across that double bond. So our definition is here, it's the grams of iodine which react with 100 grams of our fat. So the higher the number, we've obviously got more double bonds there, we've got more unsaturation. And the next page shows us a calculation involving linoleic acid and working out what its iodine number is. We're a little bit tricky in that we have to think about that definition of being in grams of iodine with 100 grams of fat. But if we were given this formula and asked what's its iodine number, one way of working it out is explained there in the red text. And so you can see that in my fatty acid I've got this on the end of it. I know that's there. So if I take that away, what am I left with? Well, it's 17 carbons and that many hydrogens. Those 17 carbons, if I was thinking of it being just an alkane chain, then my general formula for an alkane is CnH2n plus 2, so that would be 36. But because I've got this C to C bond there at the end, the most I could have is 35. So if I'm dealing with 35 but I've actually got 31, hopefully you can see that there's 4 missing, and with those 4 missing it means I must have 2 of these double bonds because there's missing hydrogens there like that. Then we get into our mole work and we can see that the answer is going to be 181. So fats, if we leave them for a long time, can go off, and we call that rancidity. 2 ways in which the fats can go rancid is when they react with water, hydrolytic, so they're getting broken up by water, giving us bad smells, unpleasant smells. That kind of smells like old feet, butanoic acid. And it could also be oxidative, so oxygen in the air could also react with parts of the molecule to form aldehydes and ketones. So sometimes to preserve these substances we might see antioxidants on a food label. Second class of lipids are phospholipids. These are the ones that make up the phospholipid bilayer in our cell membranes. And we've got, still starting off similar, we've got our fatty acid ester linked to the glycerol molecule. But on the third position, I've got this phosphate group. This phosphate group's charged, and it means that that section of it is hydrophilic, whereas these long carbon chains are hydrophobic. Cholesterol falls into the category of lipids as well, and it's also found in cell membranes, prevalent in our diet. There's 2 types of cholesterol that you've maybe heard about, HDL and LDL. And you can see here that the HDL is regarded as the good cholesterol, sort of helping clear out our arteries. The LDL tends to build up and cling to the walls, and it can lead to health problems. So cholesterol's important because it's a precursor to sex hormones, and if you look at the structure of cholesterol there, you can see that it's not a million miles away from these other steroids, estradiol and testosterone. They're sharing similar backbones. If you look at those 4 fused rings together, I should say steroids. So they are used in contraceptive pills. Steroids in males are called androgens, and androgens can be used to promote tissue growth, especially in muscles. And so people might take these to build themselves up if they are recovering from an illness, but they'll also be used by people to gain extra muscle for sporting events.